So now let's proceed with the solution to that equation. Okay, so the solution will be phi equal to a sine of square root of twice me by h cross square x, because if you remember, if you take that as say k, then it will be a sine kx plus b cos kx, but in the differential equation your twice me by h cross square comes as k square, isn't it, for a simple harmonic motion. So here it is therefore square root of, so k is square root of, isn't it? So here it is square root of solution twice me by h cross square x plus b cos twice me by h cross square x. Now what are the boundary conditions? You see, the boundary conditions are phi equal to 0 at x equal to 0 and phi equal to 0 at x equal to L. Okay. Now if you just put these values, phi equal to 0, x equal to 0, then this is sine term will be 0, cos term will be 1, but this will give you b equal to 0. Put phi equal to 0 and x equal to 0. If you put phi equal to 0, you get 0 over here. X equal to 0, you get 0 for this term. When you put x equal to 0 over here, cos 0 is 1, so you get b over here. So what you ultimately land up with is b is equal to 0. And for phi equal to 0, x equal to L, so you have 0 over here. Now instead of x, you will be writing L, so you will be getting square root of twice me by h cross square L, and plus this will be 0 because b is 0. So what you get over here is, well, so what you get over here is this one, that phi is equal, this is what you get, phi equal to 0 is equal to a sine square root of twice me by h cross square L plus 0. So you see, this is equal to 0, the whole thing is equal to 0 now. This is possible. Now a can be equal to 0, but sine of theta equal to 0 means theta is, the whole of theta is equal to n pi for all values of n, 1, 2, 3, 4, 5, isn't it? So you can write, well, square root of twice me by h cross square phi n x, okay, is a sine n pi by L into x, because you see it is a sine square root of twice me by h cross square x. So square root of twice me by h cross square is n pi by L into x. Okay, so this is what we get as solution for phi n, and ultimately you get for En. For En, what do you obtain? You obtain, therefore, because you see, over here, look over here, look and into this boxed equation. So if you take the square, you get twice me by h cross square is equal to n square pi square by L square. From there you can extract E, isn't it? So this is what you get for E, and because it is dependent on n, you put the suffix n over here for E. Okay, so En is equal to n square pi square h cross square by twice m L square, and psi n, now you can write it as a sine, okay, n pi L by x into x, and this is the time dependent part. Now how do you find A? Now you are quite an expert in finding A, because you have learned to normalize a wave function. So to normalize a wave function, what is the condition that you have to apply? It is called the normalization condition of the wave function. What is that condition? This is the condition, see. Minus infinity to plus infinity, psi n star, psi n dx, isn't it? So if you, because your psi n is a sine n pi x by L, it's a real quantity, so psi n star will be the same. So psi n star psi n is a square sine square n pi by L into x times dx, that's equal to 1. So if you take the integration from 0 to L of sine square n pi by L x dx, it's half, isn't it? It's L by 2. isn't it? From 0 to L, because it's from 0 to L, so it's L by 2. So what you get is a square L by 2 equal to 1. This gives you the value for the normalization constant. A is equal to square root of 2 by L. And now you can write psi n, the total psi n with the space and time part along with the normalization constant in this manner. Okay.